In this video, I will show you the solutions to the two-dimensional and three-dimensional particle in the box problem. First, one-dimensional box. The wave function of the particle in the one-dimensional box is the square root of a over 2 times sine function of n pi x over a. This part is called the normalization factor, so this ensures the integral of the squared modulus of this wave function from 0 to a is exactly 100%. N, the translational quantum number, can be 1, 2, 3, 4, and so forth. N cannot be 0 because if n is 0, then you have sine 0. That's 0. That means the wave function is 0. That means the particle disappears. To get the energy of this particle, we apply the energy operator, the Hamiltonian operator, to the wave function. And because the potential energy of the particle is 0 inside the box, so this really is just the kinetic energy operator. And then we get the kinetic energy of the particle, which is also the total energy of the particle. And this mass is this is the mass of the particle. A is the length of the one-dimensional box. For the two-dimensional problem, we simply just multiply the wave function in the x direction and the wave function in the y direction. And the physical meaning is simple. If you take the squared modulus of both sides, so squared modulus of psi is the probability density of finding the particle at position x in the x direction and position y in the y direction. And the position and motion of the particle in the x direction is independent of the position and motion of the particle in the y direction. Therefore, we use a multiplication here. And this guy squared to give you the probability density of finding particle at the x position. This part, the square modulus of this second part, will give you the probability density of finding particle at position y. How about the total energy of the particle in the two-dimensional box? Again, we apply the total energy operator, which is equal to the kinetic energy in the x direction and the y direction. Again, the potential energy is 0. When we apply this operator to the wave function, we get a eigenvalue here. It's simply the energy in the x direction plus the energy in the y direction. Energy is additive here. Again, this is because the motion of the particle in the x direction is independent of the motion of the particle in the y direction. So there's no correlation between the x and y direction. And over here, this is the picture of the wave function of the particle in the two-dimensional box. We have x divided by a here, so this is actually from 0 to a in the x direction. And over here, this is y divided by b, so it's just in y direction. You have from 0 to b over here. And this is a wave function. And you can see the wave function is 0 at the boundaries because the particle is completely confined inside the box. The wave function of the particle is 0 outside the box. And to ensure the continuity of the wave function, this psi has to be 0 at the boundaries. And then if you look at the x direction, so this is the x direction, you look at this, there's no nodal surfaces in the x direction. Also, you can look at the projection here. Again, we find no nodes in this x direction. So it corresponds to this n sub x equals 1. How about the y direction? If you look at the y direction, there's actually one node. Between this peak and this trough, there's one node right here. At 1/2 of b. When y equals 1/2 of b, you have a node. Very simple, you just plug this in. When y equals 1/2 of b, you get ny pi over 2, and sine ny pi over 2 equals 0. And in this case, y equals 2. So simply put, it's the ground state in the x direction, and the particle is in the first excited state in the y direction. Nx equals 1, ny equals 2. How about three-dimensional particle in the box. It's very simple. Again, you do the multiplication of the particle in one dimension. So in the x dimension, in the y dimension, in the z dimension, you just multiply the three wave functions together. Again, this is because the position and motion of the particle in the x direction is independent of the y direction or z direction. So over here, and then the total energy of the particle in the three-dimensional box is the sum of the energy of the particle in the x direction and y direction and z direction. Nx can be different from ny, and the ny can be different from nz. So all three translational quantum numbers can be different. They just need to be positive integers. And a, b, and c are the dimension of the box. A, B, that's for two-dimensional, but then you can just imagine a three-dimensional box with dimensions A, B, and C.